Welcome back, class. Now that we've had a chance to look at some stoichiometry problems and to work with some reactions using our mole ratios, I want to introduce one additional concept to this idea, and that is what's called a limiting reactant. So when we conduct a chemical reaction, typically one of our reactants will run out first, right? So we'll be doing the reaction. Let's say we have two materials that are combining. As soon as we run out of one of them, of course, the reaction will stop. And this reactant that runs out first is called the limiting reactant. And so we need to understand what this is in order to correctly do stoichiometry problems. So in the previous problems, we were assuming that whatever reactant we were given information about was the limiting reactant. And that's typically plausible. But in some problems, they will give you amounts of multiple reactants, and you have to figure out which one is the appropriate one to use. So just to wrap up the vocabulary here, before we do a few examples, is, again, the limiting reactant is the reactant that is completely consumed, right, in a chemical reaction and limits the amount of product that you can form. Excess reactants are, of course, the other reactants, right? The reactants that are present in quantities greater than needed. So, in other words, we'll still have those reactants around when the reaction stops, and they'll be there at the end. And we use the term theoretical yield to describe the amount of product that can be made in a chemical reaction based on the limiting reactant. So in reality, what we did in the last section, you were calculating theoretical yields. When we did an example to calculate how much product we formed based on the amount of some reactant that we were given, we were calculating a theoretical yield, right? So it's the maximum amount that can be made in a chemical reaction based on the limiting reactant. So it takes on a little bigger meaning here because we have to determine the limiting reactant, and so whatever we calculate based on the limiting reactant, that's what we call our theoretical yield. So now let's jump right in and do some math. So let's take our reaction here between magnesium and oxygen. So our balanced equation says that 2 moles of magnesium will react with 1 mole of oxygen gas to form 2 moles of magnesium oxide. So in our problem, we're told that 36 moles of magnesium react with 15 moles of oxygen gas, and we want to figure out how many moles of magnesium oxide are made. And in doing this, right, we want to know what's reactant excess and what's the limiting reactant. Now, notice in this problem, just to show the example, I'm only asking you to go to moles, and we're starting from moles. So we're shortening this problem a little bit, we're not having to start with grams and go into grams. So if we think about our plan for this, right, what are we going to do? Well, if we think about then, we have to go from moles of a reactant into moles of magnesium oxide. But we can't start from two things at once, right? So what comes down is we have to do the calculation twice, right? And this seems like a little bit, tedious, but it's really the only way we can do it, and it requires a couple of extra calculations. But we have to start with both moles of magnesium and calculate how much magnesium oxide we can make. And we also need to start with moles of O2 and figure out how much magnesium oxide we would make. And then once we know these numbers, right, we can determine which one is going to be the limiting reactant. So to summarize here, we're going to calculate the amount produced based on each reactant. The smallest yield is our theoretical yield and comes from the limiting reactant. So let's put that into practice. So we'll just start with the magnesium here. And so we're going to start with 36.0 moles of magnesium. And we're going to do the same types of calculations we did in the last chapter, where in order to go from moles of one thing, in this case magnesium, to moles of magnesium oxide, we have to use our mole-to-mole ratio. And so we go to our balanced equation, and we see that there is every 2 moles of magnesium, we can make 2 moles of magnesium oxide. So we have 2 and 2. And so moles of magnesium cancel, and we get 36.0 moles of magnesium oxide. Okay. So now we know the yield based on the magnesium. So now we're going to do the same thing, but instead we're going to start with my moles of O2. Again, my target is moles of magnesium oxide, moles of O2. So now I need the relationship between oxygen and magnesium oxide. So for every 1 mole of O2, I can make 2 moles of magnesium oxide. So I get 2 over 1. And so this yields me 30 moles of magnesium oxide. So now I have my 2 values, and what I'm going to see here is I'm going to look for the smallest result, and that's right here. So this is the smallest yield. That's going to be my theoretical yield that's going to come from my limiting reactant, right? Because if we think about it, the idea is that once we make 30 moles of this product, then I'm out of oxygen. And it doesn't matter that I have the ability to make 36 moles based on the magnesium. I no longer have any of the oxygen left to react with it. So at the end, we're going to be left with some magnesium there. But this is my smallest yield, so this becomes my theoretical yield. And that means the O2, right, is my limiting reactant. And of course the magnesium, right, would be in excess. Okay, so here's the basic, that gives us the basic idea. So let's do this problem again, or another version of this problem, but now let's do the full blown, right? So what if we are given grams of these things, right? This is the pretty typical. So if we outline what we would have to do, we're going to use our strategy, and it says that we're reacting 42.5 grams of magnesium and 33.8 grams of oxygen. And again, I want to know how many grams of magnesium oxide, and I want to know what's the limiting reactant, what's in excess. Okay? So what's my strategy? Well, first, since it's listed first, the idea is we're going to go from my 42.5 grams of magnesium, right? And we're going to go to moles of magnesium, and then we're going to convert that into moles of magnesium oxide, and then of course grams of magnesium oxide. And then we're going to do the same thing, but we're going to start with 33.8 grams of O2. We're going to take that into moles of O2, convert that to moles of magnesium oxide, into grams of magnesium oxide. And then we can compare these two numbers. Okay, so let's do the math. So 42.5 grams magnesium. Now remember, so the calculations themselves are going to be exactly the same as we did in the last section, right? We have to go to moles of magnesium, getting rid of the grams, right? We're going to use our molar mass, right? So 1 mole of magnesium, 24.31 grams off the periodic table. So this is going to cancel out my grams. Now I'm going to convert into moles of magnesium oxide, getting rid of the moles of magnesium. We're going to use my ratio. My equation tells me that for every 2 moles of magnesium oxide I make, I need to use 2 moles of magnesium, right? The 2 to 2 ratio. Cancel out my moles of magnesium. So now once I have moles of magnesium oxide, I can convert it into grams using the molar mass of magnesium oxide, which is 40.31 grams of magnesium oxide per 1 mole of magnesium oxide. My dimensional analysis cancels out my magnesium, and I go through my math. And if you do this, of course keeping 3 significant figures here, we end up with 70.5, neater there, 70.5 grams of magnesium oxide. Okay? So that's from the magnesium. Now let's do the same thing, but start with my oxygen. So 33.8 grams of O2. We, of course, have to convert that now into moles of O2. Now, be careful, we're using O2, right? So that's 1 mole, 32.00 grams. Now we need to go from moles of O2. We need to cancel that. We need to go into moles of magnesium oxide. Again, every 1 mole, we make 2 moles. So, make 2 moles every 1 mole of O2, so our coefficients. Now, we're going to convert into grams of magnesium oxide from the moles of magnesium oxide. And again, We did that above. We had 40.31 grams per every 1 mole. So if I check my dimensional analysis, right, grams of O2 cancel here, moles of O2 cancel here, moles of magnesium oxide cancel here, leaving me with grams of magnesium oxide. If we go through the math, this allows me, I would make 85.2 grams of magnesium oxide. So now we have our values. Now we can simply look at the two numbers and say, oh, this is my lowest. So the 70.5 grams is my theoretical yield. And magnesium here is my limiting reactant, right? Because it gives me the theoretical yield. And the O2 is in excess. Okay, so hopefully now we have a pretty good idea of how to do this, again, these same kind of stoichiometry problems, but now with this added dimension of having to actually figure out which reactant is limiting in the reaction. Okay, so we're going to keep adding a few pieces to the puzzle here. And so when we look at reactions, oftentimes we will go into the lab and do them. Well, the problem with doing things in lab is we often don't get these theoretical yields, right? Because if you've ever done anything in lab, we know that there's loss, right? We have to filter things, we have to transfer things, we have to scrape things out of containers, right? And so when we do an actual experiment and get a experimental yield, right, it is always less than the theoretical yield. And so we can calculate what's called a percent yield by comparing what would be our actual yield we get in the experiment with what mathematically we could get, right, which is our theoretical yield. So let's try that. So a reminder that our theoretical yield is the amount that we can be made in a chemical reaction based on the limiting reactant, right? This is what we get from our stoichiometry problems. We have the actual yield, which is the amount of product produced in an actual reaction, an actual experiment, right? Sometimes you'll see this called the experimental yield. And then we have the percent yield, right, which is a way that we can show how well we did, right, which is the actual yield divided by the theoretical yield times 100, right, to put it in terms of a percentage. So let's say we take that same problem that we just did. And so let's remind ourselves that, in that problem, my theoretical yield was 70.5 grams of magnesium oxide. Right? So that's what we calculated in the last problem. So 42.5 grams of magnesium is combined with 33.8 grams of oxygen. How many grams of magnesium oxide are made? Right. That's the theoretical yield. That's what we did on the last slide. 56.8 grams of magnesium are actually isolated. Right? This is another way of saying, right, what our experimental yield is, what we actually get in the experiment. What's the percent yield? So a lot of problems will be like this, right? Where they'll have you do a theoretical yield problem, and then a part B or a follow-up will be, okay, well, we did the experiment, we got this much, what was our percent yield? So we've already done the work of calculating the theoretical yield. That's the hard part. So now let's just simply calculate our percent yield. So our percent yield is going to be, again, the actual yield divided by the theoretical yield times 100. So let's plug in our numbers. We got 56.8 grams of magnesium oxide divided by 70.5 grams of magnesium oxide times 100 equals, again, three significant figures, 80.6% yield. Oops. Of magnesium oxide. Okay, so percent yield, pretty straightforward, often used as a follow-up on these theoretical yield stoichiometry problems. Okay, so I'm going to end this section with doing another example problem. So we're just going to I'm going to show one final example just to give you another problem to look at. So let's walk through this one. So we have 140.05 grams of CO, carbon monoxide, are combusted in the presence of excess O2. So now notice they've told me what's in excess. 149.63 grams of CO2 are collected. What is the percent yield? Okay, so we're after the percent yield. So let's remind ourselves that in order to calculate the percent yield, we need two things, right? We need an actual yield and we need a theoretical yield. So, what are we given here? Well, we're given an actual yield, right? That's this, right? So we have an actual yield. But we need a theoretical yield. Now, I've shortened the problem here, and again, this is just to give you different examples of types of problems you might see. Here, we're told what the limiting reactant is, right? We're said 140.05 grams of CO are combusted with excess O2. So they're telling me that CO equals the limiting reactant. So I only have to do one calculation. I need to go from grams of CO, and I need that to tell me something about CO2. So right, our follow is going to be grams of CO to moles of CO to moles of CO2 into grams of CO2. Right? So ultimately we want to get our theoretical yield in grams of CO2 here. Now, let's go ahead and get started. Now, I will caution you, one thing you should always double check. Most of the time it's fine, but we should always check, is that sometimes when they give you these equations, they're looking to see if you're paying attention, and it might not be balanced. So before you start any of the stoichiometry work, you should always double check to see to make sure the equation is balanced. Otherwise, you're going to go through the math, and it's going to be for nothing because you weren't using the right coefficients. So let's double check. So we got carbon, carbon. But look, we only have 3 oxygens on this side, and we have 3 oxygens on this side, and only 2 on this side. So how can we do that? Well, be a little tricky, right? Because we got 3 and 2, so the lowest factor there is going to be 6. Right, so we have to make it 6 on this side and 6 on this side. I'm sorry, not 6. We can, because we have oxygen in 2 different places, we can get by with doing it with only 4 on each side. So let's just see. So we can put a 2 here. That will give me 2 and 2, 4. And if I put a 2 here, that will give me 2 times 2 is 4. So we have to get them both even. That's the easiest way to do it. So we need to check that. So now let's actually start the problem. So we're going to start with 140.05 grams of CO. And of course, we have to first go into moles of CO. So we got grams of CO on the bottom, moles of CO on the top. So 1 mole of CO, 28.01 grams of CO. So now we're going to go into moles of CO2 from our moles of CO. So we're going to use our relationship. And if we look back, we see that's for every 2 moles of CO, we can make 2 moles of CO2. So we get 2 and 2. And then we're going to get grams of CO2 from moles of CO2. And that's 44.01 grams per every mole. And if we check our dimensional analysis, right, we see grams of CO cancel here and here, moles CO here, moles of CO2 here, and we're left with our desired quantity of grams of CO2. So we do the math, keeping in mind significant figures. Notice we have 5 significant figures here. Okay. So I'm going to put it down here. Now, one thing that a little bit tricky here is we have 5 here, but our molar masses are only 4. And these are not exact numbers, molar masses. You'll see different values of them. So it's a little tricky on the significant figures here, but I'm going to go ahead and just calculate this. And if we were doing it to 5, let's say, it would be 0.05 grams of CO2. Or if limited to 4, which we probably should do based on these molar masses, it would be 220.1 grams of CO2. Okay, so now we have the theoretical yield part here. So we can do our percent yield. We take our actual, right, that's the 149.63 grams of CO2 divided by 220.05 grams of CO2 equals, times 100 equals 67.998%. But probably we're more realistically at 4 significant figures based on the molar masses, and so we're going to round this to 68.00% yield. Okay, so another example of a stoichiometry percent yield relationship. So this brings our look at reaction stoichiometry to a close here. If you have questions, this, calculations can be a little bit tricky. I would encourage you to do practice problems, to look at the homework, to practice problems in the book. And if, of course, you have questions, please reach out, and we can go over specific problems that you're having problems with. Feel free to email me a problem that you're having, and I can try to give you feedback, especially, if you show me the work that you're doing, I can point out errors. We can talk through, what the problem is. So practice, and we will move on from this point to look at more qualitative type reaction chemistry as we move into Chapter 5.